Welcome to lecture number 3, R.3, Rational Exponents and Radicals. Okay, so still on the review. So the first thing we're looking at is evaluating nth roots. Okay, so the definition, an nth root denoted nth root of A is a number, B, such that the nth root of A equals B, or that B to the nth power is the same as A. Alright, once again, sort of complex definition, but we'll go ahead and use it. So for our example 1, we're going to simplify the nth roots. So we have the fifth root. Okay, so once again, the fifth root, right there, that number, of 32. So what is this asking us? Well, this is saying, is there a number that when I multiply it to itself, how many times? 5 times. So 1, 2, 3, 4, 5 times, and I multiply it to itself 5 times. Can I get 32? Does a number like that exist? And the answer is yes, there is. And that number is 2. If I multiply 2 by itself 5 times, I'll get 32. Let's go ahead and check that. Well, 2 times 2 is 4. And then we multiply 4 times 2. That gives me 8. That's an ugly 8. Okay, 8. Multiply that by another 2. That gives me 16. Finally multiply that by the last 2, the fifth 2, and we get 32. So, my answer is the fifth root of 32 is 2. Alright, let's go ahead and take a look at B. This is asking for the fourth root of negative 1. Well, let's see. This is saying, is there a number that when I multiply it to itself, how many times? 4 times, that I get a negative 1. Well, let's see. In order to get 1, I know I need to be multiplying 1 to itself. But how do I get that negative? Well, if I choose negative 1, will that give me my final result of negative 1? Let's see. Let's check this. 1 times 1, that's a positive 1. But when I multiply that by this negative 1, hey, I get that negative 1. But remember, we still have this last negative 1 to work with. And when I multiply my negative 1 by negative 1, I'll get a positive 1, which is not what I'm looking for there. That doesn't work. And it definitely won't work if I tried to make these all positive ones. So in reality, there actually is no real number that gives me the answer to this. So this has no real solution. There is no number that when I multiply it to itself 4 times, I get negative 1. So let's take a look at this next one. This next one says, what is the fifth root of negative 1? Now we might be tempted to say, like the one here, there's no answer. But let's just take a careful look. We want something when I multiply it to itself 5 times, I'll get negative 1. Let's try negative 1 once again and see what we get here. Well, the negative 1 times a negative 1, is that positive? When I multiply it by this negative 1, I get a negative 1. Let's multiply it by this negative 1. So negative 1 times another negative 1 would give me positive 1. And let's multiply it by the fifth negative 1. So negative 1 times positive 1, and that gives me the negative 1 I'm looking for. So in fact, there is an answer to this. The fifth root of negative 1 is actually negative 1. Huzzah. Alright, let me go ahead. Sorry, forgot to box my answers there. And the last one. Okay, let me clean up my work here just a wee bit. Okay. D. the square root of 9 divided by 4. Let's see. Well, the square root of 9 divided by 4, this is asking for a fraction times itself that gives me 9 over 4. Let me actually erase this real quick. I want a fraction times another fraction that will give me 9 over 4. Well, let's focus on the top. How do I get 9? What times itself gives me 9? Well, the answer to that is 3. Ew, highlighter. Okay, next one. Then let's take a look at the denominator, the bottom. So for the denominator, what times itself gives me 4? The answer to that is 2. So, the square root of 9 over 4 is 3 over 2. And that is my answer. All right, let's go ahead and move on to number 2. Simplify expressions of the form a to the 1/nth power and a to the m over n power. Okay, so 2 different forms we're going to look at here. All right, let's look at the definition. Let m and n be integers such that m divided by n is a rational number in lowest terms and n is greater than 1. All right, so what does it mean to be in lowest terms? That just means we can't simplify it. For example, 4 over 2, this is not in lowest terms. Why not? Well, this is because I can divide the top and the bottom by 2 and simplify this to 2 over 1, which is 2. Okay, so that is not in lowest terms. However, the fraction 1 over 2 would be in lowest terms because I can't divide the top and the bottom by the same number. So what happens? Well then, a to the 1 over n power is the nth root of a, and a to the m over n power is going to be the nth root of a to the m power. So notice here, the guy on the bottom is going to be the guy on the seat, and then the one in the numerator going to stay sort of in the top there. Okay, so please be careful. Don't switch those around. The denominator is going to stay as the index value, and the numerator, the m, is going to stay as the power. All right, so here we go. We're going to go ahead and simplify the following. So 25 to the half power. Well, that doesn't look quite like what we know to work with, but using this rule here, whatever is in the denominator of my exponent is actually the index or the root. So let's go ahead and translate this to something we do know how to work with, which would be this root, and what's in the denominator? That's a 2, so that, boop, is going to go right there. That's our 2. So it's going to be the square root of 25. Well, remember, the square root of 25 is asking for a number times itself. That gives me 25. And that number is 5. Square root of 25 is 5. All right, looking at the next one, go ahead and pause this video and try to translate that into the appropriate root. So the value in the denominator is 3, which means we're going to have a cube root. So this is going to be the cube root of 64 divided by 27. Now this time, this is looking for something that times itself 3 times gives us 64 over 27. So what number times itself 3 times gives me 64? Well, that number is going to be 4. 4 times 4 is 16, and then 4 times the last 4 will give me the 64. Now, what number times itself 3 times would give me 27? That is going to be 3. 3 times 3 is 9. Multiply in the last 3, and we get the 27. So the cube root of 64 divided by 27 is 4 over 3. All right, and the last one. Ooh, now notice this time, we don't have a 1 in the numerator. We have a 3. So let's see. Let's be careful here. Remember, the bottom number is going to be my index, and the top number is going to be my power. So this is going to be the 5th root of 35 to the 3rd power. Now another way to write this, which I forgot to write up top, which we're going to fill in. Another way to write this is the nth root of a to the m power. These two are the exact same thing. They mean the same thing, but there are different ways to write them. So with that in mind, let's go ahead and shift this and rewrite it to the 5th root of 35 to the 3rd power. Okay, so one thing I forgot to note here, this is actually a small typo in these notes. Sorry, that should be 32. Okay, so we're going to go ahead and change that typo on my side. Alright, so this is 32. Okay, so before we move on though, these two are both the same, so why should I be choosing this method over this method? The reason here, if I decided to do 32 to the 3rd power, that is a huge number, and then I'd be trying to find the 5th root of that huge number. A little more work than I really want to go for. If I look at this example here, this side, I want to find the 5th root of 32, which, if such a root exists, would be a smaller number than 32. And then I take that little bitty small number and I cube it, which is way more manageable than what I was trying to do if I went with this method over here. So that's why normally when you're working with things like this in math, it's good to make things smaller rather than bigger, which is why I choose to take the root first and then cube it. Okay, so once again, make numbers smaller in math. That's probably the best method. Okay, so what is the 5th root? 5th root of 32. Well, we actually already solved that. Up here, that is 2, right over there. So the 5th root of 32 is 2. All right, and that is going to be 2 raised to the 3rd power. 2 to the 3rd power is saying we want 2 times itself 3 times, which is going to be 8. So our answer is 8. Alright, so let's go ahead and simplify expressions with rational exponents. Alright, so once again, when we're doing rational exponents, ratio means fractions. So this is where we have fractions in the exponents. Now, looking at the first problem, one thing to notice is all the bases are the same, which is really nice. We can go ahead and combine them all. I'll go ahead and start with combining at the numerator, and then we'll work on the denominator. Alright, so combining the numerator, we're going to go ahead and keep the base, which is x, and then add the exponents, which is going to be 4 over 7 plus 2 over 7 over x to the 1/7. Okay, so with fractions, remember, you keep the base, and you can keep the base if they're the same. So before you add fractions, they need to have the same base. Notice they're both 7. Awesome. So we'll keep the base and then add the numerators. So we have x over, and 4 plus 2 is 6. 6 over 7, x to the 1/7. So now we have the quotient rule going on. So we'll keep the base of x, and then we'll subtract the exponents. So 6 over 7 minus the 1 over 7. So that's going to be, let's see, well, we have a subtraction problem, but the fractions have the same base. So that's great there. So then we'll just do the 6 minus the 1, which is going to be 5. So for the x, 5 over 7. And that is our answer. So now for b. Now this one's interesting. So looking at the exponent, I see three different operations. I have the negative, the 3, and the 1. Three different operations. Let's go ahead and get rid of the negative first. So remember, the negative is fish out of water. Go ahead and take the reciprocal. And we have gotten rid of the negative. Now let's go ahead and translate from the 3/4 into the rational and power form, or the root and power form. As usual, we like to take the root first because it makes the number smaller, so I'll use the 4 first, and then we'll cube whatever the answer is. So this is saying what times itself 4 times gives me 81. The answer to that is 3. So the 4th root of 81 is 3. And then we're going to go ahead and cube that. 3 cubed is 3 times 3 times 3, which is 27. So my answer is 1/27. Now, we've got this Bamboocha problem. Alright, I'm going to go ahead and, as usual, I like to check inside the parentheses to see if I can simplify. But notice, none of the bases are the same. I have a 5, a C, and a D. So I can't simplify inside on this one. And also for this one, I have a D, a 2, and a C. So none of those are simplifiable either. So what I'm going to do is go ahead and distribute in the exponent to each of the bases. Okay, so this is going to be, let's see, 5. I'm just going to go ahead and rewrite all of the bases and then do the distributing. So I have the 2, c to the half, that's the 2 and the c to the half, and then d 5/3. Alright, so I rewrote them all a little separately, and then I'll go ahead and do the distributing. So the first group gets the 2, so they all get a 2. The second group gets the 3, so they are all cubed. Alright, so now I've got a bunch of different things going on. I have power rules going on for these guys, and then the numbers are just raised to different powers. So 5 squared is 25. Then I have C and the power rule of 3/4 to second power. So that's C. We're going to multiply the power. Okay. And then same thing for all the other ones that have the power rule going on. You could go ahead and do the multiplication out on the side, but I'll just go ahead and stick it in the problem. Sometimes it's neater if you do it on the side, and sometimes it's easier because the numbers are a lot less hard to write. So notice I'm putting all the numbers that were just by themselves, I'm putting them over 1. It makes the multiplication easier. Alright, lastly I have 2 to the third power, which is going to be 8. Okay, so now I'm going to go ahead and simplify the fractions. With this one, I can cancel out the 2 and the 4, and I'm left with 3/2. So 3 times 1 is 3, 2 times 1 is 2. Now for this one, the 3's cancel, and I'm just left with 5. So the answer is 5. For the D, the 2's cancel, and so I'm just left with 1. And for the C, nothing cancels, so I just have the 3 times the 1, which is 3, and the 2 times the 1, which is 2. All right, let me go ahead and rewrite this. As usual, if you ever have any questions about any of the work in the videos, just send me an email with the problem. Make sure to include the actual problem, and I'll do my best to explain it another way. Or just further explain myself. Alright, so here we are. Let's see, I'm going to go ahead and combine these two together, so multiplying it all out. I have 25c to the 3/2 times d to the 5th power all over, and I'm going to rewrite this a little bit. I'll put the 8 first, then the c 3/2, and then the d to the 1. Now let's see. Well, the c's will actually completely cancel each other out. They're the exact same numbers. You could, if you wanted to do, go ahead and keep the base and then subtract out the exponents, which you would see equals 0. So you have c to the 0, which is 1. Or you could just do the cancellation like I did here. Up to you. Then we're left with 25 d to the 5th power over 8 d to the 1. Let's see, 25 and 8, they do not share any common numbers, so we can't simplify them. But notice, we have two base d's, so we're going to go ahead and simplify those. That's d to the 5th minus 1, which would be d to the 4th. So we are left with 25 d to the 4th over 8. One thing I want to point out now is you'll notice in my work here, look at the equal signs. They're all lined up on the side here. Okay, that is as usual to make my work neat and presentable. So please, I'm going to be going through your work. I'll try my best, at least in the first few weeks, to try to point out some notation things. But on exams, this is going to be very important so you don't get lost in your work when you're showing it to me, and also so I don't get lost in your work when I'm trying to grade. I'd like to give as much partial credit as possible, but if the work is so messy and I can't read it, then most of the times partial credit will not be awarded. So make sure to make your work neat and presentable, that way I can follow your work and understand how much of the problems you did understand, and give as much partial credit as possible. Because if you show that you understand the problem, I can give credit for what you do understand in the problem. Alright, so I have the nice lined up equal signs and I boxed my answer. Awesome. Okay, so next we're looking at simplifying radicals. For example 4, we're going to simplify the following radicals. Let's see, so we have, for part A, c to the 5th inside a cube root. What I'm going to do is see what I can take out here. Let me just go ahead and expand what's inside here. This is c 5 times. Now, I can split up radicals. This is a rule that I have. If I have the cube root of a times b, I can rewrite that as the cube root of a times the cube root of b. So I'm going to go ahead and use that rule here. Let's see. I'm going to rewrite this as the cube root. Actually, before I do that, I'm just going to rewrite this a little bit. I want to, for simplifying purposes here, I want to try and match the base of a 3. I want to try to find things in here, inside, that are perfect cubes. So to do that, I'm going to go ahead and take these 3 and write them as c to the 3rd power, and then the leftovers will just be written as c to the 2nd power. Now, once I've done this, I'll go ahead and split this up, and then I have the cube root of c cubed times the cube root of c squared. Now, here is a special thing. When you have the exact same values for the power and the index, they can so-called cancel each other, and we'll just be left with a value on the inside. Great rule to make note of. Very good. So we'll be left with c cube root of c squared as my answer. Alright, so for the next problem, we have the 4th root of 32 times x to the 9th times y to the 6th. Alright, so, as usual, this is something here. Notice our plan is to write out our perfect root values, the perfect roots, and then the leftovers when we are simplifying. I'm going to use that same plan for part B. I want to write in one radical the perfect 4th roots, and then all the leftovers in the other radical. Let's take a look at 32. Is that a perfect 4th root? Well, from what we've been doing previously, we know that 32 is 2 to the 5th power. So it's not a perfect 4th root, but it can be written as 2 to the 4th times 2. So we'll go ahead and write this in the perfect box, and the leftover 2 in the leftover box. Let's take a look at the 9. Well, let's see. We can rewrite the 9 we could go ahead and rewrite it as x to the 4th times x to the 5th. But notice that in x to the 5th we still have an extra x to the 4th power. So what I'm going to do, I'm going to go ahead and do a mini division. How many times can 4 go into 9? Well, 4 can go into 9 2 times, and the leftover is 1. Alright, so that means that I can have x to the 4th 2 times. And there's a leftover of x to the 1. Okay, so notice I was able to write this as something to the 4th power, which is my goal. Trying to match that 4. Alright, so we managed to do that with the x, with the division. So let's go ahead and look at the y to the 6th. We're going to do the same plan as we did with the x. Let's go ahead and do that division. So let's see, how many times does 4 go into 6? Well, 4 goes into 6 1 time. And we have the remainder of 2. So that means my remainder of 2 is going to be y to the 2nd power. And we have y only to the 1 power. So it'll just be y to the 4th. Oops, not the highlighter. There we go. So the base is to the 4th. Alright, so now that once we've done that, now we get to go to the exciting part, which is what we did here. We can simplify the 4. So the 4 cancels with all of those powers, because they're all perfect 4th roots, because they have the 4th power. So left with 2x squared y times the 4th root of 2xy squared. I'll go ahead and erase that extra part there. And you'll notice a lot of the times, not always, but I'll put a little tail here. That tail tells you it's the end of my radical. Just another good way to show your work neatly. I try to get into the habit of it, but it's still something I'm learning to get into the habit of myself. And there we go, boxing my answer. So let's take a look at this next problem. Alright, so the interesting thing to note about this one is we have a radical being divided by another radical. So one rule we can use here is if you have a radical with the same power being divided by another radical of the same power, you can combine them into one total radical. Or vice versa. So you can go from this method to that one, or you could change from this version to this one. So what I want to do for this problem that we have here for part C, I'm going to combine them. You might ask, why? The reason is I want to see if I can simplify them when they're combined. I want to see if I can simplify the inside. Well, let's see, take a look. We have a 3 and an 81. I know I can simplify those together. So 3 goes into 81 27 times. That's simplified. And then let's see, x to the 7th and x. I can simplify x to the 7th divided by x to the 7 minus 1 equals x to the 6th power. So these guys here turn into x to the 6th power. And then, taking a look at the y's, I have y over y to the 4th, which is going to equal y to the 1 minus 4, which is y to the negative 3. So that I'll replace with y to the negative 3. All right, let's go ahead and plug in all those things that I've simplified out. So that's going to be, let's see, 27 x to the 6 and y to the negative 3. I'll go ahead and take that reciprocal of that y, which will put it down in the denominator. So that'll be the cube root of x to the 6 over 27 y to the positive 3. Now I need to see, can I simplify with that cube? A moment to ponder. Once again, I'm going to use my arrow to show you where I've gone with my work. And I'll clean up my workstation here. All right. X to the 6th. Let's go ahead and do that division like we did previously. So 3 can go into 6 how many times? Twice. And there's no remainder. So that means x to the 6th can be written as x squared to the 3rd power. 27, well 27 is actually 3 cubed. So notice my plan is going really well so far. I've been able to write my bases as powers of 3. That's really well. We're doing really good here. Last thing is I want to be able to write y is y to the 3rd power. Well, we're in luck. It already is written as something to the 3rd power. So it's going to be y to the 3rd. And there we go. We have the final 3. So they're all written as something to the 3rd power. So once we have them all written as something to the 3rd power, we can go ahead and cancel that. And we're left with the bases, which would be x squared, 3, and y. So x squared divided by 3y. And there we go, our simplified answer. So let's look at the next one, part 5. Multiply single-term radical expressions. So for the example 5, we're going to multiply, then simplify the radicals. Assume x is positive. So for the first one, we have square root of 6 times the square root of 30. We're going to use that rule we had before, where we're going to combine them under the same radical. So that'll be 6 times 30. And then 6 times 30 is going to be, let's see, 6 times 3 is 18. Tack on the extra 0, 180. Let's see, can I simplify this? You know what I did? I made the number bigger. That's not a good plan. Let's make the numbers smaller. Remember, we always like to make them smaller if possible. Can I break 6 and 30 down? Well, 6 is 2 times 3. So the 6 is 2 times 3. And then 30, what can I break 30 into? Well, 30 is 3 times 10, and 10 is 2 times 5. So there we go. We broke 30 down into 3 times 2 times 5. Why am I doing this? Well, as usual, I'm trying to see if I can simplify my radical. And remember, in the square root, there's that little 2 hanging out on that index there. Okay? So if you don't see a number, you're allowed to assume it's 2. Always remember that. If you don't see a number on the radical, you're allowed to assume it's 2. Okay, here's my arrow to indicate where I'm going. Let's see. So I want to write things on the inside as something squared. Let's see. Oh, I have 2 2's. That means I can write it as 2 squared, because there are 2 2's. And I have 2 3's. So I can write that as 3 squared. Oh, and I have the poor little leftover 5. So let's go ahead and write this with the perfects and the little leftovers on the side. Sorry, 5. You're in the leftover bin. So my answer will be, let's see, what cancels here? Okay, so the 2's will cancel. And we're left with 2 times 3 times the square root of 5, which, when I simplify this out, is going to be 2 times 3 is 6, square root of 5. And there is my answer. All right, let's take a look at the next one. So we have a bunch of things being multiplied here. Let me rewrite this a little bit. I have 2 times the 4th root of x cubed. Can't simplify that because of those values there. Times 5 times the 4th root of x to the 7th power. What I'm going to do, I'll go ahead and combine the like terms. I'll multiply these two together, and then I'll multiply these ones together, and see if I can simplify. So 2 times 5 is going to be 10. And then I'll go ahead and combine the two radicals into 1. How come I can do that? because they have the same index value. So I'll have x to the 3 from this one, and then the x to the 7th from this one. Alright, let's go ahead and multiply those guys together. Why am I doing that? Well, remember, I'm trying to find a way to match to the 4. If I can do that, then I can simplify it. If I can't, I'm out of luck. So let's see, x to the 3rd, so that's going to be x3 plus 7, which is going to be 10. Okay, x to the 10th power. Can I rewrite x to the 10th power as something to the 4th power? Well, I don't know. Let's go ahead and do that division again. How many times can 4 go into 10? 4 can go into 10 twice. We got 2 left over. Okay, so this is going to be 10. The 4th root of, and the perfects are going to be x squared, to the 4th power, times the leftover, which comes from the 2, x squared. So we were able to match that 4 there, which means that we can cancel it. Awesome. So those cancel. We're just left with the x squared. Writing my arrow to indicate where I'm going. 10x squared times 4, the square root of x squared. Now, I don't like that 4. Why don't I like it? It's looking a little too big. So I'm going to go back, rewrite this. I don't want to confuse that 4 as a normal 4, because I might start multiplying it into my problem. Alright, let's see. That looks good. Looks like there's nothing else to simplify in the radical, so we're done. Alright. Once again, if you have any questions on any of this, feel free to send me an email. As always, give me about 48 hours to respond, especially in the more busy times of the semester, like in the very beginning or during exam times. Alright, let's go ahead and move on. Alright, adding and subtracting radicals. Okay, so this is going to be sort of a mix of what we've been doing with radicals, simplifying them, but also we're going to start adding them, so we have to think about like terms as well. So looking at the first problem, looking inside the radicals, there's no way I can simplify this, because that's to a 2 power, and the index is a 3. Since the index is a 3 and all the powers inside here are less than 3, we are sort of out of opportunity to simplify. Another thing to notice is all of the radicals are exactly the same. They're all the cube root of 7 t squared. Which means that we are in luck here because these are all like terms. I have 5 cube root of 7 t squares, and I'm subtracting from it 2 cube root of 7 t squares, and I'm adding to it, what is that? That's a 1. If you don't see something there, it's the imaginary 1. So I'm adding to it 1 cube root of 7 t squared. Alright, well what's 5 minus 2 plus 1? That's going to be, 5 minus 2 is 3, plus 1 is 4. So how many cube root of 7 t squares do I have? I have 4. 4 cube root of 7t squared. That 3 is getting dangerously large, but we'll let it live. Okay. That was pretty straightforward, because these were already like terms, so we didn't have to do much there. Let's take a look at the next problem. Right away I can tell these radicals are not the same. So I'm going to have to see if I can simplify. If I can simplify, and some of them happen to be like terms, then I can add them. If I cannot add them, then they are as simple as possible. Let's take a look. These are all square roots. So can I simplify the insides of them? For the first one, I'm not going to be writing out the 2's. The 4 can be written as 2 squared. The x, I can't do anything with that, so I'm going to go ahead and put that in the leftovers bin. And I'll bring down this plus sign. And then the y squared is a square. So I'm able to match up those for the index. Now let's take a look at the next one. The 18. Well, that is the same. Let's see, what can be 18? What numbers are in 18? I have 9 and 2. 9 is a perfect square. 9 is 3 squared. Okay, I'm able to match up that too. How about x? Poor x. X also has to go in the leftover bin again. Y squared? Hey, that's a perfect square. Okay, we're doing good. We're simplifying each of the different radicals. Let's go ahead and move on to the last one. Bringing down that plus sign over to here. We have that 3 out front. We'll leave it there, and then let's do, we have a square root x cubed. Well, in x cubed, I know there is an x squared. So I'll go ahead and take that x squared and put the leftover x in the leftovers radical. And then we have the y squared, which we can go ahead and write out the squared. Awesome. So I've managed to create the perfect radical boxes right here, which can do all the simplifying with the square root. And then I have all the leftovers hanging out on the side by themselves. Okay, let's go ahead and simplify. Those cancel, and I'm left with 2y square root of x plus, bring in that plus over to there. These also cancel. So I'm left with 3y. Bringing down the square root of x, and then the plus. Now this one, let's see what cancels. Those guys cancel, and we're left with 3xy, and then square root of x. Alright. Now you might be tempted to go ahead and add these all up real quick, but let's take a careful look, make sure they're all like terms. I have 2 y squared of x's plus 3 y squared of x's, looking good so far, plus 3 xy squared of x. So the first two are like terms because they have the same radical exponent expression going on, but the last one's not a like term. So we can only add the first two together. The last one, he's got nobody in common with him. So the first two, I have 2 plus 3, so that's going to be 5y squared of x. Plus, and the last one right here doesn't have any like terms, so we'll just leave him as he is. And there we go. We're done. Now taking a look at the last one. It's the last one for this page too, or this whole set. The last one, 3 square root of 5x. So we have square root of 5x, 3 of them, plus 2x square root of 5x's. Oh shucks, we were so close. They were almost like terms. But just because of that little x hanging out here, they're not like terms. So since they're like terms, it is already simple. So my answer is the same. We are unable to simplify. There are no like terms. Inside the radicals, we cannot simplify them. How do I know we cannot simplify them? Because they're all power to 1, and my index is a 2. Since the powers on the inside are smaller than the power outside on the index, we cannot simplify it. So we are done. It is simple. That is it. Please send me any emails if you have any questions on the material. As usual, just give me 48 hours to respond.